Thank you. So today I'm going to talk about a unique witch's brew of contaminants, hex, chrome, and PFAS. And so I can't think of a better mix we could come up with to, really do some injustice to groundwater. But in fact, it's pretty common out there. I don't know how many people here worked on hex, chrome remediation projects. Okay, not a lot. How many people saw Erin Brockovich? More, okay. Well, as you know, the state of California suffered a lot of PR issues when that whole thing went on and proceeded to really go after hex chrome contamination in California. And for years, that's been an active business for remediation. And all kinds of different compounds have been injected, from calcium polysulfide to ZVI, biological approaches, ferrous sulfate. So it's been a very active market in California. And a lot of the problems are vadose zone contamination. So hex chrome isn't new. But finding it with PFAS is a new development. It's not that new, but so why would you have PFAS for chrome plating? And the issue is that when you stand over a chrome plating bath, the hex chrome emissions are very toxic and obviously can impact your workers. So somebody came up with a brilliant idea to spray PFAS on the water baths and cut those emissions off. What happened though is that not only did they contaminate groundwater with hex chrome, they contaminated it with PFAS. So, kind of a double whammy there. And that's just a picture of a hex chrome plating bath, and they're kind of sinister. If you've ever been to a chrome plating shop, you wouldn't want to get too close to those. And then in 2019, California required that any chrome plating shop that's being investigated or characterized must be characterized for PFAS as well. So there's a lot of chrome plating shops in California and across the country. I really haven't seen much PFAS chrome plating activity in California, so I'm not sure what they're doing with this data, but it is a requirement now that it's understood that PFAS can be involved in hex chrome operations. So what I'm going to talk about today, we were contacted by an EPA contractor for a Superfund site in Texas. And they had a well-documented hex chrome PFAS plume. They had a very active citizens group and very concerned about not only hex chrome, but when they heard about PFAS, that even freaked them out even more. So the contractor came to us and said, do you have any ideas of what we could use? So first they were looking at carbo iron, which was a product made in Europe, but for some reason they couldn't get that to the US. I'm not sure what the problem was. So that fell off the table. We injected ZVI and powder activated carbon, but that was too thick of a slurry. So we really couldn't inject that very well, so that didn't work. So they came back and said, do you have a colloidal product that we could inject? And so we just happen to have one. We have a product called Colloidal Chemistries, which is colloidal carbon mixed with sodium dithionite that we use to treat TCE and PCE. And we didn't see any reason why that wouldn't work on hex chrome and PFAS. So that's what we proposed. How many people here have used sodium dithionite in metals remediation? Okay, well, that makes sense because it's not widely used, but it's been studied by DOE over the years, and it is a good reductant. It just hasn't made it to prime time like some of the other ones. And in history, it's been used for hex chrome, and it's also been used for TCE. And we sought to improve that technology by mixing it with absorption technologies to see if we could, get some good uses out of sodium dithionite. So we have a treatability lab and R&D lab, and we decided to explore this further. And we started playing around with different colloidal carbon concentrations and sodium dithionite, base activated sodium dithionite. And we saw some really good results on PCE and TCE. And the other thing is that sodium dithionite is soluble in water. So when you get to the injection phase of chemicals, their solubility is very important. The more solid-like they are, the more difficult it is to get those injected and make contact. So a colloidal carbon, which injects like a water, and sodium dithionite and caustic injects like water. So we should be able to get good distribution, which is half the battle, as you know, with in situ remediation. So the new technology, which we called AC base activated dithionite, and we do have a patent pending on that. And I'm not sure where that is. I think it's in some black hole of somewhere, but it's moving through. And it requires both activated carbon and a base. And you can use it with other compounds besides colloidal carbon. You could use it with powdered or granular. The reactions actually occur on the activated carbon surface, although we're studying that some more. And like I said, it's patent pending, US and internationally. So one of the key design parameters for PFAS with carbon is understanding their Freundlich parameters. And so these are the parameters that you use to define how much carbon you need based on your starting concentration in groundwater and what your target goals are. And we use these Freundlich parameters to help us in design. A lot of times in the industry, literature values are used for Freundlich parameters, but we felt that we had to develop our own for our product to be more accurate. We developed these and use this in the basis for our design when dosing for just PFAS contamination. As you can see, there's a list of the parameters there, but I won't go into those in much detail. Then we did a lab test on PFAS to see if, in fact, the colloidal carbon actually has the ability to absorb PFAS. And we treated 2 MCLs at a 50 milligram per liter activated carbon concentration. And batch tests were used to do this type of field design, including the flux of contaminants coming into the activated carbon, as well as what gets absorbed in the treatment zone. And you can see here we started out with 2,300 parts per trillion PFAS, and you can see the other levels for the other compounds. And then we dosed it with different amounts of colloidal activated carbon, from 25 milligrams to 50 to 100 to 200. So this stuff is expensive, so it's really good to get a good idea of how many pounds of carbon you need to meet your end game. And you can see here that we were able to meet MCLs on most of these, or non-detect. So there's no question activated carbon will absorb long-chain PFAS. So we've just demonstrated that to ourselves. And then the dosing approach for the pilot test. So we use the stoichiometric amounts to dose for hex chrome. So we came up with a stoichiometric amount for sodium dithionite. We supported that with more R&D work. And then we ended up with the field injection to demonstrate this at a pilot scale level. So we do have a model for carbon dosing for PFAS. And so, we get into a lot of detail here, but, we've got to know the parameters of, X, Y, and Z. We're really interested in mobile porosity, so how much porosity percent porosity can we inject? Obviously, the soil type is important. Fractional organic carbon is critical to what's sorbed the soil. And so those are sort of key inputs that we use in our dosing. We then look at the concentrations in groundwater, and then we estimate a KOC. Now, those are literature values. There's not many actual KOC values for PFAS out there. And then we look at the target concentration of what we have to meet. And in this case, it was the MCLs. And then finally, we look at the mass of contaminants in groundwater, in soil based on that KOC value, the mass in soil, and the mass in groundwater itself. So this gives you kind of an idea of how we dose these projects. I mean, there is a scientific basis for this. We don't use rules of thumb or anything like that. And then we actually have to make this work in the field. So this comes down to the injection design, which is, usually half the battle, maybe the whole battle. But, we looked at the different amounts of amendments that we had to inject, and we had 242 pounds of dithionite, 1,016 pounds of caustic, because this is a base-activated chemistry. And then the colloidal chem, 2,200 pounds. And then we look at the volume injected of each of the amendments and the water volume needed, and that really becomes the basis for our injection design. The other key factor, like I said, is the percent of mobile porosity that we inject. If a site has a flat gradient, no seepage velocity, once you inject, the stuff's not going to move, so you got to inject a higher percent of the pore volume. If it's got a good seepage velocity, you can inject a lower percent, and these soluble amendments will move with groundwater flow. So what do these things look like? So on the left is sodium dithionite. It's soluble. It looks like persulfate. Everybody uses persulfate. The caustic in the middle, I'm sure everybody's seen 25% caustic. Has anybody got 25% caustic on their skin? Good. It's a severe safety hazard. And then on the right is the colloidal carbon, 3 micron in a 250-gallon tote. So those are the key ingredients that we injected. How did we inject it? Well, in this case, we were going into a heterogeneous formation. So we did want some pressure capabilities. So we used the Moino pump, also known as a progressive cavity pump. That can go up to 250 psi and flow rates up to 50 GPM. And then we mix all these different ingredients in a 500-gallon tank. And then what was the delivery approach? So a lot of cases you can deliver through wells, or you can deliver through direct push, or you can deliver through open boreholes and bedrock with packers. In this case, direct push was going to provide the best results and was the most cost-effective. So we used 2¼ inch diameter tooling, and we had a 2-foot injection screen. That was a perforated pipe with an inner screen of stainless steel to make sure we didn't have any fines coming in as we drove to depth and plugged the tools. So in terms of injection documentation, well, that happens to be the site as it's being dismantled. It's interesting, I just put a proposal together for another site in California that had the same name as this company. So I think they did damage all around the U.S. So that's something to be proud of. But that was a site that was being torn down. These are how we document injection performance. We look at, the pounds of amendments that are injected overall, and we do a mass balance to see, do we have enough chemicals left based on how much we injected already. And a lot of times you can get to an end of the project and you don't have enough chemicals, or you have too much. And that raises a big issue of, what went wrong. The other thing is we look at each individual point, and we really focused on initial pressure, maintenance pressure, average flow rates, the amount of amendments injected. And so this data allows us to troubleshoot if we start seeing groundwater data that doesn't seem to be performing. And we can go back and look at the injection performance, and we say, well, we had 300 PSI here when we should have been at 100, so we fractured the formation, and obviously that's not going to go where it needs to go. So all this stuff's important in documenting injection projects. And then the pilot test results. So hex chrome was up to 71,000 micrograms per liter, and that's pretty high. PFOS was 3,100, and PFHxS was 110 parts per trillion. And so red is the baseline, orange are reductions, and green are where we met MCLs. So you can see here we met MCLs for PFAS, for all the PFAS compounds. In some cases, the concentrations came back, but we did this in the middle of a plume, so we did have upgrading contamination flowing back into the pilot test area, so that was a limitation of the pilot test. We couldn't just isolate this one area. But you can see here we got down to 1.8 parts per trillion, 0.85 parts per trillion, and then we look at the combined data. We had 98.2% treatment reduction and 92% at the two wells. There were two monitoring wells here, OB03 and OB04. And then finally, we'll look at hex chrome. And so we're able to meet the MCL on hex chrome, at least in OB03. And then we actually started to see concentrations. They were reduced, but then they're starting to come back. Once again, hex chrome is flowing into the treatment area. So we also looked at groundwater quality results. This is a little hard to read, but we looked at sulfites, sulfates, TOC, ORP, and pH. And overall, the treatment has a substantial impact on contaminant reductions and the expected groundwater parameters. But we continue to monitor those, definitely interested in sulfates and sulfides. ORP should be negative, obviously, and pH is generally going to be in the neutral range. So what's the implications for full scale? Obviously, we'd like to see this go full scale. It's a big site. Citizens are up in arms that they're being contaminated with the hex chrome and PFAS. It's a Superfund site. I believe there might be funding for it. I'm not sure. But we do believe that our colloidal chem Isker, which is the colloidal chem plus dithionite, did result in treatment of PFAS and hex chrome and down to MCLs. In the full scale, we'll have to account for upscale or upgradient contamination flowing that we have to make sure we treat, or put some kind of PRB in there to cover that flux. We saw that the caustic levels were a little, pH levels were a little lower than we'd like for activation, so we probably need to increase that caustic. And then the colloidal chem dosing should be increased just to have a higher confidence in meeting MCLs. But as you know, all these projects are governed by the budget, and so we've got to make the chemistries costs fit with the injection costs, that fit with the budget, and not always going to be 100% of full-scale treatment scenario. So the other things we need to look at And I don't know if you have experience of going from pilot scale to full scale. That's a pretty big step. And a lot of times, not a lot of thought from pilot to full scale, but there really needs to be, some serious considerations of how to take this to full scale. We need to better understand the lithology here. The lithology was a mixed bag. And so if we're going to get the contact, we have to have a better understanding of where we're injecting and what kind of back pressures and flow rates we're going to need. The locations look like they could take a high percent pore volume, so we could get more volume in the ground, which would mean better contact. Also confirmation that no other contaminants in groundwater were present that might impact the absorptive capabilities of carbon. And so we would need to do more bench testing there, because it's not just hex chrome and PFAS in that groundwater. It's a mixed bag of stuff. And then as we move to full scale, we like to take manual injection technologies and switch it over to automated technologies, so we have precise control of pressure and flow, so that we get the best contact possible and the best distribution of these amendments. And that's it. Thank you.
All right.